Good news, everyone. This is Mr. Mull. Today we're going to look at a problem where a projectile is launched not horizontally, but at an angle that's not zero. So we're going to go ahead and get started here today. So the question says you kicked a soccer ball at an angle of 40 degrees above the ground, and it has a velocity of 20 meters per second. Okay, so my velocity is equal to 20 meters per second. And I'm going to assume that because it's at an angle, that really is my resultant velocity. It doesn't say anything about just vertical or just horizontal. So the ball is moving 20 meters per second, and it's at a 40-degree angle from the horizontal. So we're going to find some stuff about it, and we're going to start with drawing a motion map for this object. So when I look at the object's path, it's going to go up and then it's going to come back down, just like we've seen on whenever we see a ball being kicked. We're going to assume that there's no drag. Notice that the blue is representing the vertical component of my velocity. So I'm going to change my color, make it a little darker here. Okay, so in blue is my v sub y. In red are my v sub x's, my horizontal. And then this green in the center is going to be that resultant velocity. And I've drawn that in for each part in this object's motion. At the center, you'll notice the velocity vertically is 0. That's when it reaches the tip of the trajectory. And then it starts coming back down, and you can see the overall velocity in green. And you'll also notice that the acceleration is the same for every single one of these, because remember, as soon as it leaves the ground, the only force acting on it is gravity, and that's the net force. It doesn't change. The ball is the same mass, so the net force is the same as it soars through the air. The acceleration is going to be constant, -10. So once we've drawn our motion map, what we have to do is we have to start looking at this mathematically. So I'm going to take that first kick. Okay, my resultant was 20 meters per second. So there's the y component and the x component. And to solve those, we're just going to use some trig. And as you can see on the right here, when we plug that all in, we're going to find that the y component is 13 meters per second. That's how much of the kicks is going to send the ball in the vertical direction, and then the horizontal piece is moving 15 meters per second horizontally. You can also consider that the v sub x is actually the average velocity, and this v sub y was going to be our initial velocity, VIY, because that is what the velocity the object had when we first kicked it. So once I have this information, I'm going to start looking for some things that I know to solve for some things I don't know. And the first question says, how high will it go? So if we look at the top here, we're trying to figure out what is this height at the top when it's at the highest point. And I know that that's really just a delta y. It's a change in the change of position from that 0 point. So I'm going to find delta y, and that's what I'm looking for. And I know that it starts out vertically at 13 meters per second. That was the initial vertical velocity. Because we don't have to worry about horizontal velocity at all, because it's acting independently of the vertical velocity, we're going to ignore the horizontal stuff right now and just deal with what's going on vertically, because it happens independently of whatever's going on horizontally. So at the tip top of this path, I know that the object is not moving up or down, so we're going to say that its vertical velocity at that point is 0 meters per second. We're going to call that v sub fy. And when I know that it's not moving at that top, I actually know another piece of information. So when I plug in what g is, solve for delta y, and my initial velocity, I can use this equation here. When we rearrange it to solve for y, we end up seeing that the delta y is a positive 8.45 meters. So we found how high it was going to go based upon all the vertical stuff that's going on, because that's the only thing we're concerned about when we're dealing with how high the object is moving. It's a vertical. So the next question is asking, how much time does it spend in the air? Now there's a couple different ways to do this, and I'm going to show you each way. First thing we can do is we can break up the problem into the two halves. And if I look at the problem, I notice that there's the way up, there's the way down. And because we have our friend symmetry, what happens on the way up is going to happen on the way down, only a little different. But in the center, I know that, as we said last time, it's going to be not moving at that central point, so 0 meters per second for the final velocity. The initial velocity y is still 13, g is the same, and we're going to solve for delta t instead. So because I'm talking about the final velocity, and this is at the midpoint, okay, that's at the midpoint, I'm going to plug this into our equation, rearrange to solve for delta t. When I do so, I'm going to find that it takes 1.3 seconds to change a velocity to reach 0 meters per second at the tip top. So it took 1.3 seconds to get up to here. So all we have to do is just multiply that number by 2, because it's going up and down, and we're going to get our change in time was 2.6 seconds. It takes twice as long because it has to go back down again. The other way we can do this is we can look at the initial and final vertical positions of the ball, final and initial, and because the displacement, delta y, for the whole motion, I can think of the whole arc as 0 meters because it ends up where it started. So with that information, I can go ahead and use my first equation and plug in 0 for delta y, and then I can rearrange the rest of my equation, getting delta t eventually by itself. And in this second to last step, you'll notice that you divide both sides by delta t, and the square goes away here. And then we're going to be able to eventually get down to delta t. And then when we do that, we're going to find out that it took 2.6 seconds for the object to go up and come back down with that information. Okay, that way it works totally fine. I'm going to show you another way in a second. But let's keep going. The next question says, how far away from you will it hit the ground? This is talking about the horizontal range. So the biggest key here is that the time in the air is what connects both vertical and horizontal motion. While everything happens independently, when the projectile is not in the air any longer, the motion is over. So that 2.6 seconds, that delta t, is going to help us when we know that horizontally at the beginning it was moving 15 meters per second. That was the average velocity horizontally, and it was moving 2.6 seconds, so we can just find out that it was 40 meters was the range of the projectile. I also wanted to show you that the last piece, a third way. Question D. What is the ball's velocity when it hits the ground? Hey, who is your friend? Symmetry is your friend. So if my velocity initially was 20 meters per second here, as it comes back down, it loses 10 meters per second of velocity vertically as it goes up, and then it adds, and then it gains that velocity back in the negative direction on the way down. So if this was 13, it's going to be 10 less here, and it's just going to keep decreasing depending on your time interval. As it comes back down, it's going to have the exact same velocity when it hits the ground. It left with 20, assuming no drag, it's going to land with 20. Okay, so 20 meters per second is going to be my final velocity, my final resultant velocity. Put a little r there. The last thing I want to show you is that because we know the final velocity is the same as the initial velocity, we can actually solve the time in the air problem one different way. And we can go ahead and say that our displacement is 0, like we said, but we're going to actually add now that our final velocity is going to be negative 13, and we're going to look at the entire arc, not just halfway. And so because this is negative 13 and this is 13, what we can do is we can use the equation we used for method 1 and just plug in our value for initial velocity and final velocity. And when we do that, we actually get the time for the entire path. So that's just another way you can do a question to do that, part B. Okay, so this was a lot, and when you come in on class, I'm going to expect that you have these noted out, and you're going to be ready to try one of these on your own, and I hope that this was helpful.